Okay, the reciprocal function. This is part A and part B. I think we'll do part A tomorrow, and we'll do part A today and part B tomorrow, and then also do the test review tomorrow. So reciprocal functions are functions that are basically flipped upside down. There's a couple different ways to think about them. If you have some kind of original function, you could think of it like you're taking it to the exponent -1. That's one way to flip it upside down. Another way to flip it upside down is obviously just put it onto the bottom. And if it's some kind of fraction, it flips. So if it was a over b, it's going to become b over a. So start to flip these things upside down, and this is really a lead into what you're going to do in grade 12, which is rational functions. So we're going to look at the entire function of these and how they kind of work. I don't really like this definition, so I'm going to skip it. Examples, we just did some examples of different ways it could look. Really, it's anything with a polynomial on the bottom will probably count as a reciprocal function. So let's take the first example, and this is an investigation. So first, let's start with just the line, and everybody knows the line y equals x. That's our horizontal, our 45-degree line, where every x value is the same as every y value. So if x is -10, y should be -10. At -5, it's -5. -2, it's -2. It's literally the exact same. Y is the same as x. So -1/2, -1/5, -1/10, 0, 1/10, 1/5, 1/2, 1, 2, 5, 10. So the first thing that's probably giving you alarm bells is why the heck do they go by such weird numbers on the left here? That's not really normal for any function we've looked at so far. Because when we do this, it's going to be important. Because it gets really, really near our restriction is going to be the important part there. Okay, so let's fill in 1 over x. So this is the reciprocal function. If we multiply these two things together, they end up equaling 1. That's another way to think about them as well. So we can say a lot of things about reciprocal functions. Okay, so all we need to do is do 1 over our x value. So our very first one should be 1 over -10, which is the same as -1 over 10. We pull the negative to the front. Don't leave it on the bottom. Next one is -1/5. Next one is -1/2. Then it's -1. Now what happens if you do 1 over -1/2? So it's like you're dividing by a fraction, which means you flipped upside down. The 2 actually joins the top in this case. So this is actually -2 now. This one's going to be -5. This one's going to be -10. And 0, what happens if we do 0? So 1 over 0 is going to be undefined. So we've talked a lot about restrictions this year so far. We did restrictions on radical functions, so the inside of the root cannot be negative numbers. I think we did a bit of you cannot divide by 0 in our last unit. And here's just that restriction again. So you can't divide by 0, and we kind of get that idea already. And then we go the other side, and it should be all the same numbers, just positive now. And flipped, of course. So 10, then 5, 2, 1, 1/2, 1/5, 1/10. Okay, I assume the next question is to graph this. Well, let's answer some questions. What's unique about the reciprocals of 1 and -1? Well, let's look at those ones. At -1, it stayed the same. At 1, it stayed the same. So it's actually invariant. Those are invariant points, which means that they're points that after the transformation, after whatever you did to the original function, they did not change. They stayed exactly where they were. That's going to be a big part of the grade 12 curriculum as well. Why do they stay the same? Well, if you flip over, it doesn't matter whether one's on the top or one's on the bottom. It doesn't really matter. Yeah, it's going to be the exact same thing on both sides. Doesn't really affect it in any way. Okay. Oh, this is completely different. Yeah, that's not going to help us. What is the reciprocal? Why is the reciprocal of 0 undefined? Cannot divide by 0. That's just not allowed. That's a rule. What happens to the value of the reciprocal as the absolute value of a number increases in value? Well, that's a tricky question. So I assume we're going to talk about as it increases in value into really, really big numbers. So as x approaches infinity, we might say, then 1 over f of x approaches. What actually happens? So as our x values get really, really big, we're talking about this guy, you get smaller, 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 and if we extended that really, really far, you could probably guess it's going to go towards 0. And this is going to be in the calculus unit. You start taking limits of functions. So we would say the limit as x approaches infinity, and we talk about the horizontal asymptote from there. Actually, that'll be in 30-1 too a bit. Okay, use the coordinates to sketch the graph of the function. So both functions on the same grid. Well, the one is really easy. Our first one is just y equals x. That's just our horizontal line. I don't think I have a ruler here, so I'm just going to rough sketch it. So that's our line y equals x, the perfectly 45-degree line. Every x value is the same as every y value, and all those things are true in this line. Now the other one is going to be quite different. I don't think I have my values here, but I think I know what it looks like. So we started at, actually I need to look, -10. Do we have 10 lines? We do. And that starts at -1/10. Starts way down there. And then at 5, I think it's there, it's at -1/5. So still very, very close to the 0 line. Hasn't grown much at all. At 2, it's -0.5. And at -1, it's -1. That's one of our invariant points. And then at 1/2, it's 2. At 1/5, it's 5. 3, 4, 5. And at 1/10, it's 10. So it has this kind of, I don't even know what you would call this shape. It seems to be stuck by the two axes. It seems to approach them really, really close. And this is true. This is going to be what we call an asymptote. I'm sure we've talked about asymptotes before, but if we haven't, I'm going to just say it all over again. We're going to do it down here. An asymptote is a line on a graph which is never ever touched, but is always, always approached. And that is going to be right here. We always do them with dotted lines, and here. So there's actually two. There's a vertical and a horizontal. It will get closer and closer to them without touching. Let's connect these dots together before we do the second half. We need arrows on the end there, and it doesn't bounce back or anything. It only ever gets closer to those dotted lines. It's never going to just start going off in a different direction. It's just going to get really, really close. Okay, doing the other half, it actually starts up here, then here, then here. our invariant point, and then it starts going this way. So it has almost the exact same pattern, just this time in our first quadrant. And we connect those dots together. And that is our 1 over x line. And this is kind of our parent, we call it, of all of our reciprocal functions, or all of our rational functions. This is the first one we want to think of, and all the rest are kind of transformations of it. So you have to get really used to its shape, you have to get really used to its features, and one of its key features, so usually when we talk about graphs of functions, we talk about the points it travels through. And there are two that are really important, of course. It goes through 1, 1, and it goes through -1, -1. Those are two very important key points, and they kind of anchor the whole function. But also, there's really important axes of symmetry. Even though they're not actually on the graph, they do define the graph in a very significant way. Why does the curve approach the y-axis but never touch it? The y-axis, why does it approach that? Because you're never allowed, x is never allowed to equal 0. That's from our restriction. Since x is never allowed to equal 0, it can never actually touch that vertical y-axis. Why does the curve approach the x-axis but never touch it? Because the whole function can never equal 0. There is no solution to this problem. And we're going to look at a lot of these in grade 12 especially, but we're going to start looking at them now. The only time a rational function is equal to 0 is if the top is equal to 0. So the bigger number we put on the bottom, if we put 10 there, it's really small, 100 there, it's really small, 1,000,000 there, it's really, really, really small, but it will never quite be 0 because the top can never be 0. The only time it can be 0 is if the top is 0. So it will never actually touch either of these axes, even though we'll get very close to them. Neither are actually possible. And that's what we say down here. It has two completely different, distinct parts to the graph that don't touch each other. And these are located on either side of the vertical asymptote and the horizontal asymptote. Now these could change depending on what values we have in our function. Right now they're at y equals 0 and x equals 0. Asymptotes, a line whose distance from a given curve approaches 0. That's a weird way to say it. I like my way of saying it better. I would say it's a line for which the curve always approaches but never reaches. Distance to the curve approaches 0. That sounds like the line is moving. The curve is what's moving. Vertical asymptotes occur at non-permissible values of reciprocal functions. And we saw this in our last unit, right? Oh, actually, maybe we didn't. This is in the 30 unit. So anytime you have a value in the bottom that cannot be canceled out, that's going to create a vertical asymptote. And horizontal asymptotes describe the end behavior. We say end behavior of the graph, or the behavior as it gets very large or small. So I guess that's redundant putting the end there. But usually we just say end behavior. We'll just say that. What do the ends of the graph look like as they get really, really big and really, really small? And we're going to analyze that more in grade 12 as well. Okay. Last 2 pages. Characteristics. So let's just keep on talking about this because this is our most important one. Domain of y equals x. All real numbers. Domain of y equals 1 over x. All real numbers, but x is not allowed to be 0. There's one break in the graph. There's only one question you can't ask it. You're not allowed to ask it, what are you when x is 0? It'll just mumble at you and it won't know how to answer. Range, y equals x, all y's. There's nothing wrong with the range. It can give you every possible answer. What about our rational function? Can it give you every possible answer? Well, they're all real numbers, so long as y is never 0. It can never give you the answer of 0. That's the only thing it's never allowed to be. It will shoot up forever and down forever. End behavior. So what happens when x approaches infinity, and what happens when x approaches negative infinity, is the way I like to write that. When x approaches infinity in the first function, y equals infinity. And when it approaches negative infinity, y equals negative infinity. So it goes really, really high, goes really, really low, basically is what we're saying there. Infinity is not a number, but it is a concept, and it's a concept we can understand fairly easily in math. Same question of this guy. When x becomes really, really big, it approaches 0. If x can actually go to infinity, y actually will be 0. You can never actually reach infinity, so you'll never actually reach 0. But this is actually perfectly fine to say mathematically. And when we go to negative infinity, what did that look like on our graph? So as it approaches positive infinity, it goes towards 0. As it approaches negative infinity, it also goes towards 0. Now it goes towards 0 from the negative side, but we don't actually worry about that too much. We can just say 0. In calculus, we're going to be a bit more specific. We would say this approaches 0 from the top, and we would say this approaches 0 from the bottom. So it'll never actually be 0. It'll always be numbers slightly bigger than 0. And this one will never actually be 0. It'll always be numbers just slightly less than 0. But we'll learn that in calculus. I'm not expecting that for this course. Behavior at x equals 0. Interesting. Now we're going to write this one in. So I would do it this way. Actually, I don't know any other way to put this. So maybe we are actually going to use this language. I didn't think it would ask this question. I would say as x approaches 0 from the left, as it approaches all the numbers just to the left of 0, what actually happens? So there's our 0. Everything to the left, as it approaches it from this direction, it goes towards negative infinity. And x, oh sorry, this is over here. I'll just keep going, but this is for our rational function. There's nothing special about the behavior of this one. At 0, it's just 0. I'll switch it. I'll just say when x equals 0, y equals 0. That's all it is for this one. There's no weird behavior there. In our rational function, as it approaches 0 from the right, so approaching 0 from the right, but approaching 0, not going this way, not going to the right, starting on the right and approaching 0. While it shoots up, it goes towards infinity. Positive infinity this time. So sign does matter. If you put the wrong signs there, I will mark you wrong. Invariant points, so points that don't change. Well, we have 1, 1, and -1, -1. And this kind of comes about from our rule that a reciprocal function times its original function will always equal just the line y equals x. So that means that this green line here, on your original function, any point that touches this green line will actually be there on your reciprocal function too. Those will always be your invariant points, I think, if I'm remembering correctly. I believe so. Yeah. They occur at any point where f of x equals 1 or f of x equals -1. Actually, so it's a little bit different. Whenever your original function equals 1 or whenever your original function equals -1, then when you flip it upside down, it shouldn't actually change the values. It should actually stay the same. So that's actually not the green line that creates invariant points. It's actually these two. It's a vertical line at 1 and a vertical line at -1. Okay, graph the reciprocal of a linear function, 2x plus 5. What is its reciprocal? Well, its reciprocal, 1 over f of x, we could call it, or we could call it f of x inverse. I probably prefer this way. It's a little bit faster to write, I think. So it's the function inversed is equal to 1 over 2x plus 5. Okay, that's not too bad. Determine the equation of the vertical asymptote of the reciprocal function. So where is the vertical asymptote here? That's where our restriction is. So we should actually state the restriction here. This is not a complete expression until you state the restriction. So x cannot equal -5/2. So there is a vertical asymptote at x equals 5/2, -5/2, sorry. The sign does matter. That's it. Whatever the restriction is the vertical asymptote. Unless there's something on the top that can cancel it out. That's the only exception, which I don't know if we're going to see. Okay, last question. Graph the function and its reciprocal on this graph. So to graph the reciprocal function is a little bit complicated. First, let's graph the original function, 2x plus 5. We've been doing this since grade at least 9, right? So it starts at plus 5. And from there it goes 1 to the right, 2 up. 1 to the right, 2 up. And just connect that into a line. Something like that. Okay, now we want to graph the reciprocal function. So first we want to draw vertical asymptotes. So usually we like to pull out a color and actually draw a dotted line in with a little bit of color so we can see it really easy. So at -5/2, which is -2.5. That's our vertical asymptote right there. Determine horizontal asymptotes. So these occur when x approaches infinity or x approaches -infinity. And we can actually sub this in and do some quick math with it. I really actually enjoy math with infinities quite a bit. Because a lot of the calculations, if you can kind of see it intuitively, they just go like super, super fast. So what happens if we let x equal infinity here? So if we let x equals infinity, this is 2 times infinity, which is still infinity. Add 5 more to it, still infinity. So this is infinitely big on the bottom. So what is 1 divided by the biggest number you could ever think of? Well, that's going to approach 0. So for this one, y is going to be approaching 0. What happens if we sub to -infinity? So -infinity times 2 is -infinity. Plus 5, what happens there? Well, infinity is too big to care about this. So -infinity plus 5 is still -infinity. It doesn't really get bigger because it's so small, it doesn't even matter. It just shrugs it off. So now it's 1 over -infinity, which is going to be 0 again. But we might want to note that one's 0 from the top and this one's 0 from the bottom. Because that number is always going to be, when you're doing -infinity in here, it's going to be 1 over a very big negative number. It's going to be negative going towards 0. So we can kind of tell what side it goes to. Okay, so there is a horizontal asymptote then. Let's draw that in. at 0. And I like to put in the end behavior as well. So we said as x approaches infinity, it approaches 0 from the top. So it's going to look something like that. And x approaches negative infinity, it approaches 0 from the bottom. So we have our end behavior right there. And we can kind of probably guess the rest, but we're going to do a bit more. Mark the invariant points. So when does y equal 1 in the original function? When does y equal negative 1? Let's make sure I have my points correct. So down 2, 1 left, down 2, 1 left. So yeah, that's an invariant point right there. Down 2, 1 left, and that's an invariant point right there. So that's our positive one, that's our negative one. Those points are not going to change from our original green graph. And then what else do we need to do? Mark the reciprocal of any y-intercepts or max or min values. We don't have any max or min values, so we don't have to worry about that. But if you had like a quadratic, you'd want to find out where the vertex goes to. We do have a y-intercept, which is at 5. So its inverse is going to be 1/5. So that already should be way down there. All you have to do is take the y value and flip it. Same thing with this guy up here. This is at like 9, so this is going to go down to 1/9. We could actually find all these points really, really quick. Really, really small one here, like 1/100, goes up to 100. So actually this is going to go up that way. Really small negatives, it's going to become really big negatives. So basically it just connects all together like this. Something like that. It can be hard to draw a really good graph, but we can hopefully do a pretty good job with it. That part right there, I wish I had it back. I was trying to draw it from a distance so you could see. Sketch each branch of the following using the following information. When f of x is positive, 1/f of x is positive. We can kind of already see this from the graph, but this is good to point out. Whenever our green function was in the negative, our purple has to be in the negative. Whenever green was in the positive, our purple has to be in the positive. And then really quickly you're saying to yourself, well, what happens when the green is 0? When green is 0, you make your vertical line. That's the point it's never allowed to touch, because you can't divide by 0. So the line breaks at the red line, and then everything either goes into the negative or everything goes into the positive. When f of x increases over an interval, 1/f of x, what happens? So this whole function is increasing, actually. We always talk about it as we're moving to the right. The entire green function is always increasing. What is our purple function doing as we move to the right? Well, this is actually decreasing. And then this starts back at the top, but this is decreasing as well. So when the green function is increasing, the inverse is decreasing. And we could guess if f of x was decreasing, the inverse would increase. So these are some kind of quick rules. I don't know if you necessarily need those. If you've done these first 4 points, you should already have a pretty good idea of what the graph is going to look like. So this isn't super easy to do, but it's not too hard either. Complete the following table. The zeros of this is -5/2. That's the point where the y value is 0. Vertical asymptote, there's none. Horizontal asymptote, there's none. Y-intercept at y equals 5. Oh, sorry, y-intercept is at y equals 5. Domain, x is real numbers. Range, y is real numbers. So nothing special about that, it's just a line. This guy right here, zeros do not exist. It never actually hits the x. So I got the graph up here. Never actually hits the x-axis. It will never have a 0. Vertical asymptote, make sure you write this as a line. That's one of my pet peeves. A lot of people just write the number, -5/2. I always like to see it as a line. Asymptotes are actual dotted lines. So the vertical asymptote is this vertical line. How do we write the equation for that? I always think for my vertical or horizontal ones, these are special cases. What's always true for this one? Well, the y is changing, but the x is always -5/2. So it's that line. Horizontal asymptote when y is 0. What is the y-intercept? Where does it touch this right here? That's actually at a 5th. Domain, x cannot be -5/2. Range, y is a real number so long as y is never 0. 0 is hard to find out. This is probably the only one that we can't really see just by looking at this thing, where the horizontal asymptote is going to be. But there's going to be a quick rule when we get into grade 12. Basically, it's always going to be 0 if the bottom is bigger. If the bottom is a bigger degree function, it's always going to approach 0. So the only way we can make it not 0 is if we added a number to the outside. If we said something like +2, then this part would approach 0, but the horizontal asymptote would end up going up by 2. So it would actually be 2 then. So most of our cases it's going to be 0. Sometimes you might have vertical shifts, which change the horizontal asymptote. And when in doubt, don't necessarily trust that because we haven't learned all those rules yet. Just sub in positive infinity and negative infinity and see what number you're getting close to. Okay, that's it for that. Start this homework, and then we'll do the last lesson another time.